Bombs contain heavy metals like lead, tungsten, or uranium to increase their effectiveness and lethality. These metals are dense, allowing them to penetrate targets more easily and cause greater damage. When bombs explode, the heavy metals fragment into shrapnel, spreading over a large area and causing more casualties. Some heavy metals, like depleted uranium, are heat-resistant, ensuring they remain effective in extreme conditions. However, these metals also leave toxic residues that can contaminate the environment, creating long-term health and ecological risks. Bombing and military activities release heavy metals into the soil, which can be toxic to humans and the environment. Analyzing soil from bombed areas will reveal elevated levels of these metals compared to non-bombed sites.
Following the Israeli bombing of Lebanon in 2025, particularly in the southern regions, we collected 2 soil samples from different affected areas, one from Khiam, a village in southern Lebanon, and the other from Beirut. These locations were selected to compare the impact of contamination in a rural versus urban setting.
By analyzing both samples, we aim to determine whether the same types of bombs were used in both areas or if different explosives were deployed. Our analysis will focus on identifying the presence of toxic substances and heavy metals in each sample to assess whether they contain similar contaminants or distinct compositions.
How these pollutants affect agriculture productivity, we planted parsley in both soil samples and monitored its growth. Observing variations in plant health and development will help us understand the severity of soil pollution and its implications for food safety. Through this research, we hope to provide valuable data that could contribute to soil rehabilitation efforts and raise awareness about the long-term environmental consequences of war. Soil samples were collected from a depth of 3 to 15 centimeters because this range allows us to assess whether the soil is contaminated. This depth was specifically chosen since rainfall has been minimal this year, reducing the likelihood of deeper infiltration, and because the war is still recent, meaning contaminants have not had sufficient time to penetrate deeper into the soil.
Visited the Industrial Research Institute to test these heavy metals in these samples.
Did not test for ammonia and phosphate because it is commonly used by gardeners as a fertilizer for plants, making it an unreliable indicator of detecting the use of toxic bombs. 3 different plants were planted under these conditions to compare the effect of different contaminants on parsley growth. The experimental setup will allow you to observe how heavy metals and normal soil affect parsley in various ways. Here's why this experiment is valuable. This plant grows normally with healthy green leaves and strong roots, showing us parsley thrives in clean, balanced soil. It serves as our comparison, helping us see the effects of phosphorus and heavy metals on plants' health. This reminds us that unpolluted soil is essential for agriculture, food security, and environmental balance.
Planted a parsley plant with phosphate to observe how elevated phosphate levels affect the plant growth. Phosphate is an essential nutrient for plants, aiding in root development, energy transfers, and overall growth. By increasing phosphate levels, we could study the plant's response to an experiment with excess nutrients, helping us understand the potential impact of nutrient imbalances on plant health and growth. This experiment also highlights the importance of maintaining balanced soil conditions for optimal plant development and sustainability.
This plant struggles to grow because cadmium and lead are toxic metals that disrupt its natural functions. They interfere with water and nutrient absorption, causing stunted growth, yellowing leaves, and weak stems.
During our visit to the Industrial Research Institute, we examined the soil samples for heavy metals. Typically, lead levels should range from 0 to 50 mg per kilogram, but our samples revealed concentrations between 100 and 10,000 mg per kilogram, significantly exceeding safe limits.
Similarly, while cadmium is normally present in levels of 0.1 to 1 mg per kilogram, our findings ranged from 0.5 to 50 milligrams per kilogram. These elevated readings indicate severe contamination, which not only impairs plant growth and soil health, but also poses a major risk to the food chain and human health due to toxicity of these metals.
Heavy metals like lead, cadmium, and mercury contaminate our soil, posing serious risks to plants, animals, and humans. Once in the soil, these toxic elements reduce fertility, disrupt plant growth, and enter our food and water supply. In humans, heavy metal exposure leads to severe health issues, including brain damage, kidney failure, and cancer. Animals are also affected, as bioaccumulation disrupts their nervous system, reproductive health, and overall survival. Unlike other pollutants, heavy metals do not break down over time, making contamination a long-term environmental threat. Understanding these dangers is crucial so we can work towards preventing pollution and protecting both nature and the human health.
As a solution, different types of beneficial microbes were created to help clean up and restore agricultural soil. When these microbes are applied to soils with heavy metals, they break it down and turn it into usable compounds, which plants and other organisms can absorb. After several treatments over a few months, the soil becomes safe again and ready for farming. National biotechnology offers an environmentally friendly and sustainable solution to soil contamination.